Welcome everyone to today's webinar. My name is James Wiken. I'm a Senior Application Engineer at the MathWorks. And today we're going to be talking about time series anomaly detection for predictive maintenance. Now before we go any further, I want to just show a quick example of what this can look like. So what we have here is a dashboard that's connected to 4 different assets that we're looking to monitor. Now each one gives us data every few seconds, and with that data we can detect whether it's operating normally or whether there's an anomaly happening. Now, how exactly we're testing that? Well, that's what we're going to build today. But the idea is that we can monitor this data as it comes in, detect these anomalies, and then use them to determine some sort of overall health of the device over its operation. If it goes too low, we take it down to fix it. If it stays high, then we know with some confidence that it is behaving as it should. All right. So anomaly detection is just one type of predictive maintenance algorithm, and it's often one that we're going to get started with. And all it's really just trying to tell us about is whether or not things are working as they should, or if they're not. Now, this can be helpful, but oftentimes we want to go beyond just this simple yes, no. And that's where we start moving into sort of deeper predictive maintenance algorithms like diagnostics, where we can ask, okay, it's not working, why? Now, this is still just in the current state of things, so there's no predictive power here. But that's, when we get into prognostics, or more specifically, remaining useful life estimation, where we can say, this thing will probably fail within this time frame. Now, as we move down this list, we get increasing value from it. As you can imagine, being able to know why something's failing, or even able to know that something is going to fail before it fails at all, is quite useful. But in order to get to that point, we need more and more data in order to build those models. And more specifically, we need labeled data, where that data isn't just some sensor data we happen to gather and store somewhere. It's something that we've gone through, we've processed, we've labeled accordingly, so we know what is an anomaly, what isn't. And that's where a lot of organizations need to start, and that's where anomaly detection comes in. So even if you want to get down to the bottom, which most do, we're going to start up at the top in order to enable ourselves to get to that lower point. And there's other benefits for doing anomaly detection beyond just doing what we need to in order to get to those other strategies. We can use it for things like process monitoring or predictive maintenance directly in order to be able to monitor assets and to detect faults in real time. They can also be used for things like quality control or just analyzing test data as it comes in, beyond just standard statistical metrics or visual inspection. Okay. So I've said anomaly detection a few times. Let's talk about what exactly I mean by that. So there's different types of anomalies out there. Some are relatively straightforward to be able to pick up, even without any sort of specialized tools or techniques. Things like point anomalies, or outliers as they're often called, can be detected pretty easily, either through statistical methods, or I can just look at it and be able to pick it out. But there's more complex anomalies as well. So moving into things like collective anomalies, where the anomaly isn't a single point, but rather a series of points, and maybe across multiple different time series. And sometimes the anomalies will only manifest when we're looking at those time series in conjunction with each other. So those are often referred to as multivariate anomalies. And in order to be able to recognize those, either you need a lot of experience, sometimes even decades of experience, just staring at that data, or building out some of these anomaly detection algorithms in order to help enable that sort of exploration. But at the end of the day, we're really just looking to answer the question, is something different happening than what I would normally expect? All right, so there's a few different approaches that we can take in order to do this sort of anomaly detection. Things like statistical or distance-based metrics, where we're able to just sort of calculate numerical values in order to tell us whether things are normal or not. Oftentimes we can get started there because it doesn't require as much data, or going into actually building a model to support it. But there's some other model-based approach like one-class AI or clustering we might do as well. Now, you may not be familiar with this sort of one-class AI idea, where we're operating under the condition that we mostly just have normal data. anomalies are few and far between because we've designed our system to work as it's expected to. And so one-class AI allows us to be able to use that normal data in order to train those models without necessarily needing a large amount of anomalous data in order to get there. We'll talk about the specifics of that when we get to that example. But these fall into two pretty broad cases for anomaly detection. The first is just data exploration. I've got a mountain of data that I've collected over time, and I know there's probably anomalies in there somewhere, but I don't either have the time or expertise to go through and sift it all by hand. And so I want to be able to explore those patterns quickly and efficiently so that I can pick those needles from the haystack and find those anomalies with some confidence. Now, once we have that, we can start building up a small but hopefully growing over time data set where we've actually labeled those anomalies. And even when we just have a few of them, that's when we can start moving into that AI algorithm development option where we're going to train a model like one of those one-class AI techniques I mentioned before in order to be able to make predictions on new data from what I've already learned from my historical data. Now, in this situation, we still have a wildly unbalanced data set. The vast majority of data is just going to be normal data. And so we want to use what few anomalies we've detected as efficiently as possible. So it's going to be used to do the actual testing of these models once they're trained, but all of the training data is going to be done on normal data, at least in the techniques that we're using today. So I have an example for each of these. We'll start on the data exploration side because realistically that's where you'd probably start if you were starting from relatively scratch. And then we'll move into actually building a few models with some of this data as well. Okay, so for the data exploration side, we're going to be focused mostly on the pattern and statistical techniques. Even more specifically, we're going to be working with some of these functions we see listed down here, where we're going to be calculating various distance metrics in order to determine whether a sequence of data is normal or there's sort of similar patterns in our larger data set, or if it's anomalous, it's sort of unique in the larger data set. A key thing to note, there's no trained models here. There's no labeled data requirements. And as I mentioned before, we're probably going to be using this technique to start getting that labeled data in the first place. So for example, today we're going to be working with some current data off of this servo motor. It's just rotating at a constant speed, and we've collected this data so that we can start to explore it. We'll bring it into MATLAB. We'll start to use some of these distance-based techniques in order to pinpoint anomalies in a larger data set. All right, so going into MATLAB, let's first load our data in. And just to be upfront on this data doesn't actually have anomalies that we gathered, so we're going to inject some synthetic ones. Now, there's some benefit to doing this. If we know where they are, we can test to see how well these methods are working, to see if they can pick out the things that we know exist. Now, realistically, we wouldn't be injecting our own, right? We would be looking for ones that actually exist in the data, but for demo purposes, that's what we're doing. All right, so the first thing we're going to do is going to call this distance profile function. Now, all the functions here that we'll be using are relatively new additions to the tools. And this first one allows us to do a bit of exploration with our larger data set. What we see here, and actually let me just pop this out into its own window, is a few plots. So the first one up top, this is just our standard time series. And we've highlighted the sort of subsequence that we're looking to compare against other parts of the time series. Now, the second one, this is the distance profile. So this is essentially computing the distance or the difference from this highlighted subseries with the other ones throughout the entire time series. So we can see this data is fairly periodic, so the distance is also periodic. It gets closer when it's sort of lined up and farther away when it isn't. Now, a couple other things that we'll highlight here. So this yellow, this labeled motif, this is the most similar other subsequence in the entire data set. So we're saying orange and yellow match the best. And then the purple is the discord. This is the one that matches the worst. And oftentimes, if there are anomalies, they'll be sort of highlighted in this purple as we sweep through sweep through this data. We can see that kind of shows up in different places, but often comes back to that section. Now, the bottom plot here is just looking at the sort of calculations for determining where that yellow and purple show up for the subsequence I've selected. So note the x-axis here is different. But what we're looking for is we can see that the query, or the orange, lines up nice with the yellow. So if you can't see it, that's because they're lined up pretty perfectly here. Whereas the purple is quite a bit different. So it's showing that there's this anomaly here. So why don't we switch to the anomaly itself, and we can try to compare it. So once again, we're looking at the sort of orange dotted line up top here. And one thing you'll notice is that it doesn't track well with either. So this shows me that there really isn't a close fit for this particular data section. So once again, kind of pointing me at this is probably an anomalous bit of data. Now this is a nice exploration tool, but it does require me to kind of come in here, drag things around, and try different stuff. If I want to start moving towards automating this is when I would move from just the sort of distance profile that I create into this matrix profile. So I'll run this, and we'll take a quick look at what we have here. So a lot of these plots are very similar to what we saw before. I'll pop this out again so we can see it full screen. And what it's highlighting is the sort of the biggest discord, or the biggest difference, or the biggest anomaly in the data, which is this sort of purple section here. It's also highlighting the sort of most similar pair. And down below we can see yellow and orange are lined up almost identically, whereas purple is very different. Once again, showing that this is another anomaly. So we were talking about this one over on the right before. Here's another one. I can see a big gap in the data, so kind of no big surprise there that there's an anomaly. And we can go one step further, right? This is just showing me the top one. But if I want to pick out multiple, I can come in here, I can specify, pick out the top 3, calculate these distance metrics again, and then use this find discord function in order to find the top 3 anomalies in that metric. And if we look at this, it gives us a few locations. So we get 1618, 3009, and 718 here. And if we scroll all the way back to the top to see where we added those anomalies in the first place, we can see we added them at 720, 1600, and 3000. So it actually picked it out quite nicely. All of them are within plus or minus 10 within where those anomalies actually started. So this is just a quick look at it, but these are some of the techniques that we can start to employ in order to find anomalies in a larger data set. I can go through, highlight these, label them accordingly, and then repeat as more data comes in to start building up that labeled data set that I need for any of the other techniques that I want to employ, whether it's still within anomaly detection or eventually going all the way to condition monitoring and remaining useful life estimation. All right, so the next thing we're going to do is we're going to move into the other use case, which is that AI algorithm development. So we've moved along a little bit. We've matured a bit in our data where we've got at least a small set of labeled anomaly data that we can use. We're going to take a look at how we can use that data effectively within this sort of development workflow. So if you haven't seen this before, it's pretty standard where we acquire data. We might do some pre-processing or cleaning of the data, and then we get into the actual modeling part of it, where we first need to do some feature engineering, where we're going to take our sort of standard time series data and then convert it into some data points that can be used to then train an AI model. Now you might be thinking, why don't I feed just the raw time series in? Well, a lot of these machine learning models aren't necessarily designed to just take a raw time series in. We're much better served doing a bit of feature engineering to extract the important information out of it so that we can train our models more effectively and more efficiently. I'll go through how exactly we do that and how we start exploring what features to keep and why as we get into the example as well. But Once we have a model trained, that's when we can actually deploy it, use it in the real world, and start to build out things like the dashboard I showed at the beginning. So we're going to come back into MATLAB in a second, but here's the example data that we're working with. So this is some 3-axis vibration data, so it's 3 time series instead of the 1 that we were working with before. And we have it broken out into a bunch of different chunks. So you can see here that we've essentially buffered the data into 70,000 sample sections. And what we want to do is we want to label that 70,000 points as a anomaly or not. So that whole subsequence is going to be classified as one thing or the other. So we'll bring that in. We'll do some feature extraction from that sort of raw time series data. We'll then use that to train some of these 1-class models and then validate them against the anomalies that we labeled in the earlier part. All right. So switching over to this example here, the first thing that we're going to do is we're going to load our data in. Now, as I mentioned, this data is basically a bunch of 70,000 long time series in sequence. And each one of them has a label. Either it was gathered before maintenance happened, so generally it's anomalous, or after maintenance has happened, in which case it's operating under normal conditions. Here's a quick look at some of the data. So the blue here is the sort of anomalous data, and the orange is the normal data. So before and after refers to before and after a maintenance event. So we're assuming after maintenance, everything is working as it should. And you can see, there's some visual distinctions, right? There's a little bit of shift between them here. There's these sort of big spikes in the orange that seem to have sort of smoothed out in the blue. But, even though I can visually see some things, how would I, represent these in the model that we want to train? Well, that's where we go into the feature engineering side of it. So to do this, I'm going to use a tool in MATLAB called the Diagnostic Feature Designer app. So this can be found up here in the Apps tab. If I come up here and search Diagnostic Feature Designer, it'd be right here. And I actually have this open already. And once it's open, we'll start a new session and we'll select our current data set. So the data set in question is this trained data. And we can see here that it's our 3 time series, 1 for each axis of vibration. Now, once we brought this in, we can start to look at how we want to, start extracting features or work with it. So, for instance, I can just start with like a signal trace, and we can, get a look at some of the signal data that we're working with here. Now this will look pretty similar to what we had before, but it might look a little messy because this is all of those different samples overlaid on each other. So, this is, comes with the question, there's a lot of data to parse through. How do I extract these features? Well, this tool is really aim to help make this a bit easier. Now, to do this, I'm going to move over to the right here, and we're going to go into this feature generation section. And I'm just going to start by generating some standard sort of signal features. Now you can see there's many other options here. And this tool actually provides a ton of different options for feature extraction. We'll start with just this section, and we'll just leave everything on and hit apply. So it's going to go through. It's extracting 40 different features from each signal. So I think we'll have 120 in total. And it'll display some histograms of a few of the top features here once it's all loaded in. This is working with a not enormous data set, but a fairly large one. And we can see some of these histograms here. All right, so what do we see? Well, each of these features, we're seeing both the before and the after. So the after is blue, the before is orange in this case. And what we really want to see is we want to see separation between the two. We don't want to see a lot of overlap. And unfortunately, in at least the ones we're seeing here, there's a lot of overlap. which means that we're not able to cleanly separate between our two classes with that particular feature. Now, it's okay. I don't expect every feature to be useful. Really, the goal here is to try to extract as many options as possible so that we can turn around and pick ones that are actually useful to us. Now, I just extracted those, relatively small set of features, the 40 features we had here. If I wanted to just try everything, I can. There's an auto features button here where I could just have it try everything. Do signal stats like we just did right now, frequency-based things, system identification, or curve fitting based approaches. There's a lot of different options there, and there's even some specific stuff for rotating machinery as well. And so if you don't really know, or you just want to have everything out in front of you, this is a great way to just take that initial shot in the dark and get everything out in front. I'm just going to stick with these because we're really just kind of showing this as an example. And we'll get to the next step, which is ranking the features. So I'll select this rank features. I'll choose the feature table that we created in sort of the last step. And what this will do is it will use a ranking algorithm to tell me which of these is the most useful or sort of most information rich from, in comparison to each other. So we can see here there's, a few that show up at the top. And at this point, I might, select just the top 12 or 10 or however many I want to keep. Or maybe I have some threshold that says, oh, the score needs to be above this value in order to keep it. It's really up to me. And there's a lot of, trial and error and experimentation at this stage in order to see what can work best. Now, the one we see here is this sort of t-test. But if we come up here, there's a lot of other options as well. So not only are there a ton of different features you can extract, there's a tons of different ways that you can sort them and kind of choose which ones are most useful to you. All right, so that's how we would do the sort of initial exploration of feature engineering. As I mentioned, there's potentially a lot of experimentation here in order to try to figure out what works best for a particular problem. We're going to kind of skip over that and move to a set of features that were determined before to be good separators. So here's some of those histograms again. And unlike the ones we saw before, we can actually see orange and blue are fairly distinct in where the peaks happen in almost all of these. This one doesn't as much, but all the other ones look pretty significantly different. And so if you want to see, here are the sort of top 4 ranked features for each channel based on our analysis of this, and the ones that we end up keeping. Now, what we did is in that tool, you can then have it generate code for you in order to extract those features. So, this is what that code looks like, and you kind of scroll through it to see more past these comments, but this is the result, which is this table of our features. All right, so now instead of a bunch of 70,000 long time series, each one of those has now been essentially compressed into a 12 feature or 12 value vector of features for each of those. So a huge amount of data compression for when we actually get into the training, and that's important, right? We started with, as I mentioned, a fairly large but not that large data set for sort of determining these features, but what we would then do is we would turn around and apply that same feature engineering or feature extraction techniques on my complete data set or a larger data set or a data set that grows as I gather more data, and actually use that for the training as we go. So that's what we're doing here. We're essentially loading in a complete feature set from a larger data set. And as I mouse over this, we can see we've moved up from, I think it was 40 rows of time series up to almost 18,000 rows of time series. So if you can imagine the size of that data if we kept it in the original time series structure as opposed to these features. All right, so once we have them loaded in, we need to prep them for actually training our model. And a big step of that is separating it out into a couple of different sections. So we're separating it out into a training set and a test set, okay? Test set will take about 10% of the data, and the training set will be used for the other 90%. Now, there's an extra wrinkle of this because we're doing that sort of one class AI I talked about before, where all of our anomaly data is going to be used only in the test set, right? It's not going to be used in the train set at all because we honestly don't have enough in order to balance it against the normal data that we do have. So as I mentioned before, we want to use that where it is most useful, which is in the testing part of this. Okay, so once we've done that, we can actually go into training one of these models. So let's hop back into the slides for a second before we do the actual training and talk about some of the different techniques that are available. So this is not a complete list, but it is the list of the few that we're going to be going through today. There's a handful of other ones that are available in the tools as well. But the first one is a one-class support vector machine. So what this does is essentially draws a boundary between the two halves of the data, the sort of anomaly and not anomaly. So this works well if the data cleanly separates, but if there's a lot of overlap between when something is an anomaly and when it isn't, it's difficult to draw that boundary with a high level of accuracy. Another option is this isolation forest. So what this is doing is essentially building a set of decision trees and determining, sort of where they branch off. And if they branch off early, then they're generally more anomalous because they kind of don't follow the same pattern as a lot of other things, whereas if they go down deeper, they don't. And then the last one is this LSTM autoencoder. So this is a deep learning approach where we're going to take that original data set. We're essentially going to train a representation of it that can then be used to reconstruct the data. And the idea is if we're only doing it with normal data, then it can reconstruct normal data well. But if it gets anomalous data as an input, well, then it can't reconstruct that original data well. And so we can determine how off it is. And if it's off by a certain amount, then it's considered anomalous. All right, so those are a quick and dirty explanation of each of those. Let's see them in action. So for the one class SVM, we just feed it that normal feature set. So once again, only normal data being used for the training. Once it's trained, then we're going to bring in that test set, which has both anomalous and normal data in it to test how well it did. And we can see it actually does quite well. So, over 99% accuracy. So in this particular data set, anomalous and normal data separates quite nicely, at least in the features that we've extracted. So that means we probably did a fairly good job in our feature engineering in order to let this happen. And so, it performs well. Let's look at the isolation for us. So this one's maybe a bit more robust when things don't separate as cleanly. And if we scroll down, we're doing that same strategy, right? Only normal data for training, and then a mix of anomalous and normal for testing. And we can see this one doesn't do quite as well, right? It's around 92-ish% overall accuracy, so a bit of a drop. It just happens to be that this particular problem is more well suited to the SVM than the isolation forest. Now, obviously, there's fine tuning we could do. We could do things like hyperparameter optimization or various other training options that we could set in order to fine tune this. But at least on sort of first pass, these are doing fairly well in terms of determining what's anomalous versus what isn't. All right, let's move over into the LSTM option. And this setup is going to be pretty similar to what we saw before. We're going to bring in the data. We're going to separate out so we're just working with the features. So this is the same feature set that I was working with before. It's just named a little bit different. And we can see a little bit of the imbalance here. So, all of the after data makes up, is like twice as much as the before data. And there's not even all of the before data is necessarily anomalous. So this is the sort of off balance we're talking about. And honestly, if you're just getting started with this, it's probably even worse than that. That same sort of splitting into training and testing happens. And then we just use the normal data for the actual training of the model. All right, so here's where we actually define the model. So we're going to use this deep signal anomaly detector object. So this is a sort of convenience object that's available in order to build out one of these signal anomaly detection algorithms, specifically using a deep learning approach. Now, for this, you can either use a convolutional neural network or an LSTM. These are different types of deep learning models, and we're using the LSTM one here and sort of setting these parameters. Don't worry too much about the specifics, just know that we're creating this LSTM-based autoencoder. Once we've done that, we're going to specify our training options here. So these are just making sure that it runs for not too long or will converge properly. And then we'll train it using this, this train detector object here off of the training data. So I ran this beforehand because it takes on my laptop, like 8 to 10 minutes to train, and I'm not going to have you sit here and watch that. But we can see that the loss function here, which we want to go down over time, does indeed go down over time and kind of levels out near the end of the training. Let's do a little bit of testing on this. So we'll feed it some of the data that we've had before that we separated out for testing, and have it determine, the amount of anomalies in the data and whether it's able to capture them. So to do this, we're going to call this detect function on it, and what it gives us is a couple of different ways to visualize this. So this one is visualizing the loss of a specific anomaly. So this is that 12 feature set for one of our time series, right? So originally this was like a 70,000 time series. These are the 12 features that represent it. Now this is a no anomalies detected situation, so this is a normal one. And we can see here that the raw signal, which is the blue, lines up pretty nicely with the yellow, right? No big differences between the two, and we get this overall loss of 0.49. If we scroll down, this is an example of an anomalous one. So we can see the loss has jumped all the way up to 2. And especially at the end here, we can see a pretty clear separation between the sort of the raw signal or the reconstructed signal and the anomaly itself. So it wasn't able to reconstruct the signal properly because it was anomalous data. Now, we could look at this at sort of a higher level, where really all we care about is just that loss value. We set some threshold that says above this threshold, it's an anomaly, and below it, it's not. And we can set that manually, or when we train this detector, it calculates one as well. So in this case, it calculated one at 0.56. So anything above 0.56 loss is considered anomalous, and anything below it is not. And we can see here sort of the separation. So what we see on the left, this is mostly the before data. And remember, we looked at it's about 1/3 is before, 2/3 is after. So here's our before, here's our after. And we can see there's a ton of anomalies in the before and just a few in the after. Another way to look at this is you can sort of plot the loss distribution over over like a histogram of it, and we can see that we get this threshold that pretty cleanly separates between the two histograms here. Just to try to compare apples to apples here with the other techniques that we used, here's a confusion matrix where we want things to be on the diagonal to be accurate, and we can see overall it's around 97.6% accurate, so a little bit less than the SVM happened to be, but this one will probably be more resilient against them not cleanly separating, whereas the SVM wouldn't be. All right, so that's just a few examples. As I mentioned, there's some other options for AI techniques as well, and all these were one class. Just a reminder, right? So we're only using the normal data to train them. As our data becomes less and less unbalanced, as we gather more and more of the anomalous data and label it accordingly, we can start to move into other options, 2-class or n-class techniques, and that's when we actually start moving beyond anomaly detection into things like condition monitoring and eventually into prognostics and remaining useful life. Now, for any of these models, anomaly detection included, we do want them to get out into the world where they can actually run. And so to enable that, you can deploy these trained models in a couple of different ways. If you're looking to deploy them on the edge, say you have some embedded hardware that's out on the factory floor or out in the field next to the asset, and you need your model to run there, then we offer code generation tools that you can use to take the models that you developed in MATLAB and convert them into low-level languages like C, C++, or HDL to deploy into those types of hardware. Or if you want it to sit next to the sort of the database or the data storage and want to run it on some sort of IT or OT system in the cloud or on an on-prem server, then we support that as well through our compiling tools. You can compile things either as their own standalone executable or as a software component or a service API that could be integrated into a larger application. Now, this was just a quick look at some of the options that are available for doing anomaly detection with MATLAB. If you need more support or you want to continue this discussion, we have a number of ways that we can help you. Feel free to reach out. We can do guided evaluations or training, or even go all the way to consulting engagements in order to help you adopt these techniques in your day-to-day. All right, and that's all I have for you. So thanks for attending the webinar,